Derivation of the identity, 1 plus dollars backslash cot2, a equals backslash CSC2a. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already mastered. In our previous lessons, we explored the most fundamental identity in trigonometry, which is sine squared a plus cosine squared a equals 1. Building on that foundation, in this current subsection, we are going to move one step further. We are going to derive another crucial Pythagorean identity, one that specifically relates the cotangent and cosecant ratios. Now, you might wonder why this matters. Well, mastering this identity is essential because it provides us with a powerful tool for simplifying complex trigonometric expressions and solving intricate geometric problems that you will encounter later in this course. So, let's get started with the derivation. Understanding the foundation. Now that we've recalled our fundamental identity from the previous slide, let's look at the foundation we need to build our new identity. To derive this, we're going to start with a simple right-angled triangle, which we'll call triangle A, B, C, where the angle at vertex B is exactly 90 degrees. To make our calculations clear, let's define the sides of this triangle specifically in relation to angle A first. Side B, C is our perpendicular side, which is the side opposite to angle A next. Side A, B is our base, which is the side adjacent to angle A finally. Side A, C is our hypotenuse, which is the longest side, located directly opposite the right angle. Now we apply the Pythagorean theorem, which is the core principle we'll be manipulating in the next few steps. This theorem tells us that the square of the hypotenuse is equal to the sum of the squares of the other two sides. In our specific triangle, we can write this as a b squared plus b, c squared equals a, c squared. Keep this equation in mind, because in the very next slide, we are going to perform a specific algebraic step to transform this theorem into the trigonometric identity we are looking. Step-by-step derivation. Our goal here is to transform that standard Pythagorean theorem into a trigonometric identity that specifically involves cotangent and cosecant. To do this, we need to manipulate our equation so that we create ratios that match the definitions of cotangent and cosecant, which we will see in the next slide. Let's look at step 1. We start with our Pythagorean equation, where a b squared plus bc squared equals a c squared. To get the ratios we need, we are going to divide every single term on both sides of the equation by the square of the perpendicular side, which is bc squared. When we perform this division, our equation becomes a b squared over bc squared plus bc squared over bc squared equals a c squared over bc squared. Moving on to step 2, we can simplify this expression to make it much cleaner. First, we can rewrite those squared terms as the squares of entire fractions. So a b squared over bc squared becomes the fraction of b over bc all squared. Next, look at that middle term, bc squared divided by bc squared. Since any non-zero value divided by itself is just 1, that term simplifies to 1. Finally, we rewrite the right side as the fraction of c over bc all squared. So our simplified equation now looks like this. The fraction of b over bc all squared plus 1 equals the fraction of c over bc all squared. This sets us up perfectly for the next step, where we will substitute our trigonometric ratios. Now that we have established our foundation using the Pythagorean theorem in the previous slide, let's move into the actual derivation. Step-by-step derivation continued. Now that we have successfully divided our Pythagorean equation by the square of the perpendicular in the previous step, we move into the most rewarding part of the derivation. Step 3, where we substitute our trigonometric ratios. Take a moment to recall the fundamental definitions of the ratios for angle A that we've studied before. We know that cotangent of A, which is cot A, is defined as the ratio of the base to the perpendicular, or AB over BC. Similarly, cosecant of A, written as CSCA, is the ratio of the hypotenuse to the perpendicular, which is AC over BC. Now, let's look back at the simplified equation we reached on the previous slide. If we substitute these specific ratios into our equation, the term for base over BC squared becomes the square of cot A, and the term for AC over BC squared becomes the square of CSC. This gives us the equation. Cot A squared plus 1 equals CSC A squared. Finally, in step 4, we move to our final notation. In trigonometry, to keep our work clean and professional, we don't usually write the square outside of parentheses. Instead, we write cot A squared as cot squared of A, and CSC A squared as CSC squared of A. By rearranging the terms slightly, we arrive at our finished identity. Cot squared of A plus 1 equals CSC squared of A, or more commonly, 1 plus cot squared of A equals CSC squared of A. We have officially derived our new Pythagorean identity. Domain of validity. Now, before we move on to see how this identity is used in real-world engineering, we must discuss its domain of validity. This is just a mathematical way of asking, are there any angles where this formula actually breaks down? As you can see on the slide, this identity is valid for all values of angle A, as long as angle A is greater than 0 degrees and less than or equal to 90 degrees. You might be wondering, why can't angle A be exactly 0 degrees? Let's look back at the triangle we used in our derivation. If the angle A were to become 0 degrees, the side BC, which is our perpendicular, would shrink down to a length of 0. Now, remember our definitions from the previous steps. Cotangent of A is the base divided by the perpendicular, and cosecant of A is the hypotenuse divided by the perpendicular. In both of these ratios, the perpendicular, or BC, is in the denominator. If we try to plug in 0 for BC, we end up attempting to divide by 0, which is mathematically impossible. Therefore, at 0 degrees, these specific trigonometric ratios are undefined, making the identity invalid at that exact point. Real-world application example. Now that we have mathematically derived the identity and understood its domain, you might be wondering, when would I ever actually use this in real life? It's easy to view these formulas as just abstract symbols on a page, but in reality, trigonometric identities are vital tools in professional fields like civil engineering and architecture, where ensuring structural stability is a matter of safety. Let's look at a practical scenario. Imagine you are an engineer tasked with designing a support brace for a tall tower. In many construction phases, you might not have the exact physical measurements of every beam yet, but you do know the proportions of the structure. If you know the ratio of the base of the brace to the height of the tower, which, as we learned in our derivation, is the cotangent of angle A, you can use our identity, 1 plus cotangent squared of A equals cosecant squared of A, to quickly find the ratio of the brace's length to the tower's height. This allows you to calculate the cosecant of angle A without needing to manually measure the actual lengths of the beams on site. To break down the logic of how we apply this, first, we start with our given information, which is the ratio of the base to the height, represented as cotangent of A. Our goal is to find the ratio of the brace length, which is the hypotenuse, to the height, which is the cosecant of A. To do this, we simply apply the identity. We square our known ratio, add 1, and then take the square root of that result to find the cosecant of A. It's a powerful way to use proportions to solve complex structural problems. Key takeaways. All right, let's take a moment to recap everything we have covered in this lesson to ensure the concept is clear. First, it is vital to remember that the identity, 1 plus cotangent squared of A equals cosecant squared of A, is not just a random formula. It is derived directly from the Pythagorean theorem that we know so well. To recap the process we just walked through, the derivation is achieved by taking the Pythagorean equation, ob squared plus bc squared equals ac squared, and dividing every single term by the perpendicular squared, which is bc squared. This specific step is what allows us to transform side lengths into trigonometric ratios. The real power of this identity lies in its utility. This identity allows us to find the value of cosecant of if cotangent of A is already known, and vice versa. It creates a direct mathematical link between these two ratios. Finally, a quick reminder on the limitations. We must remember that the identity is undefined when the angle A equals 0 degrees, because, as we discussed earlier, that would lead to division by 0 in our ratios. Now, before we wrap up, let's look at some common pitfalls that students often encounter during exams. Common mistakes to avoid. First, watch out for confusing your ratios. It is quite common to accidentally swap cotangent A with tangent A. Always remember the fundamental difference. Cotangent A is the ratio of the base to the perpendicular, whereas tangent A is the ratio of the perpendicular to the base. Keeping this distinction clear is vital for using the correct identity. Second, be careful with your algebraic steps, specifically regarding division. A frequent mistake is dividing the Pythagorean theorem by the square of the base, ob squared, instead of the square of the perpendicular, bc squared. If you were to divide by the base, you would actually derive a different identity. 1 plus tangent a squared equals secant a squared. While that is also a valid identity, it is not the one we are focusing on today, so ensure you are dividing by the perpendicular to reach our target formula. Finally, pay close attention to your notation regarding exponents. Please ensure you use cotangent a squared and not cotangent of a squared. It is a subtle but crucial difference. The square applies to the trigonometric ratio itself, not to the angle inside the parentheses. Now, as we wrap up this lesson, I want to pause and highlight some common pitfalls. Even if you understand the derivation we just walked through, it is very easy to make small errors during exams. If you can avoid these 3 mistakes, you will have a much stronger grasp of these Pythagorean identities. Great job today!